Okay, so welcome to what is this? The fourth week of senior stream. And so last week, in case you weren't here, we covered binary search trees, binary searching on functions, and real numbers. And so at the end, I gave you a couple of practice problems for you to do. And in hindsight, they were a bit difficult for someone who's new to binary search. So what we're going to do today is I'm going to take up two of the practice problems that I assigned to you last week, and then we're going to jump into prefix summaries. Okay, so the first problem was CCC 2015 S3 gates, and the problem says, for your birthday you were given an airport, and the airport has G gates numbered from 1 to G. P planes arrive at the airport, one after another. You are to assign the ith plane to permanently dock at any gate 1 to a GI, for where GI is between 1 and G inclusive, at which no previous plane has docked. And as soon as plane cannot dock at any gate, then the airport is shut down and no future planes are allowed to arrive. In order to keep the person who gave you the airport happy, you would like to maximize the number of planes starting from the beginning that can all dock at different gates. So let's just take this sample input to help us understand. So the first number here is the G value. So this is the number of gates. So we have 4 gates, number from 1 to G. So 1, 2, 3, 4. And so this 3 value is the P, so the number of planes coming in. So the first plane, so the GI value of this plane would be 4. So that means we can place it anywhere in 1, 2, 3, or 4. So let's say we put it at 3. So no other plane can dock at gate 3 now. And so the second plane coming in has a GI value of 1. And so the only gate that we can put it is 1. And so no other plane can dock at 1 anymore. And the third plane coming in also has 1, and so it can only be docked at gate 1. But obviously we've already had a plane at gate 1, so we can't have that. And so the number of planes we can dock is 2. So the key observation in this problem is that we should dock the planes at the highest available gate. And that's because, say we docked plane 4 at 1. So if we had 1, 2, 3, 4, and plane 4 came in, and we docked it at 1, and so 1 is no longer available. What would happen when plane 1 comes in, or the second plane comes in, and it has a GI value of 1, it would find that 1 is already taken, and it can't dock anywhere. So our answer is 1 instead of 2, and that's not optimal, right? We know the optimal value is 2. So we want to dock each plane at the highest available gate. So it has a number that indicates how it indicates how far it can go. So if it had a value of 3, then you know it can only dock at 1, 2, or 3. And if 3 is not available, then we make it dock at 2. And so I guess the intuition behind this is that the lower gates are more likely to be useful to us in the future because you don't know what planes are coming in next, right? So they could be 1, and they can be 2, but the lower the gate, the easier it is for us to use it for the future planes coming in. So the problem reduces to given a set of available gates, find the one with find the highest one that can be used to dock the plane. Whoops. Okay, so how we can solve this is by using the data structure binary search tree, which is implemented in C++ as set. So set int would give us an ordered set, and we talked about this last week about binary search trees. So our algorithm becomes, so we're going to maintain an ordered set of available gates. And so now we need to process the query of finding the highest one that can be used to dock the plane. So we need to find the highest element in the set that is smaller than or equal to gi, where the gi is the value that the plane can dock at. So it can dock at any gate from 1 to gi. So if we look at the functions of an ordered set, we'll see that lower bound gives us the element that is greater than or equal to gi, and upper bound gives us the element that is strictly greater than gi. But what we actually want is the element that is smaller than or equal to gi. So you'll see that this is what we want is smaller than or equal to, but we're only given a greater than or equal to or greater than. So neither of these functions can help us as is. So instead what we can do is we can insert negative values of the gates. And so, for example, if I had -1, -2, -3, -4, how the set would order it would be in increasing order like this. And so now if we use the lower bound function, it would function just like greater than or equal to when we flip it over. So I'll demonstrate that when I go and implement it. So we insert negative values and use lower bound. Okay, so let's declare our variables. I'm going to initialize a variable called answer to keep track of the number of planes we can dock, and we're going to process p planes. And so we're going to use the lower bound function. So we have to maintain a set of available gates. So before we process any queries, let's insert all of our available gates into our set. So it starts at 1 and goes to g. And we're going to say gates.insert -i to insert the negative values into there. And how that's going to, the reason we do that again is because lower bound only help us find the greater than or equal to operation, but or condition I should say, but we actually want smaller than or equal to. But if we flip the sign of the values, then it'll work the opposite of what it's supposed to be when we flip it back. So let's just use the lower bound function on the gates, and we're going to search for -gi. So we know that lower bound returns the gates.lower bound something returns gates.end if it didn't find anything. And so if it didn't find anything that was available, that means that the airport has to shut down, so we have to stop. So if it is equal to gates.end, then we're going to break out of the loop. And otherwise, we're going to increase our answer as well as erase this gate from the from the set of available gates. So gates.erase. And finally, we just output our answer. Okay, let's try this. Okay, so that worked. Are there any questions? Okay, all this code will be posted on GitHub later if you want to take a look at it afterwards. But for now, if there are no questions, I'm going to move on to the second problem that I assigned. So, um, that's slower than usual. Okay, so this problem says there are n people taking part in an eating contest, and so they each have consumption coefficient of AI, and they're also trying to eat n plates of food, and so the difficulty of each food is Fi, and so the time it takes for a person with coefficient AI, or let's say a person with consumption coefficient X, and a plate of food with difficulty y would be x times y seconds. So it takes x times y seconds for that person with that consumption coefficient to finish a plate of food with difficulty y. And so what we want is to minimize the longest time that it takes for a person to finish the food. So out of all n people, what is the minimum x times y that is possible? And also they add another twist to it, which is that they can do training, and in one set of training they can reduce their consumption coefficient by 1 as long as it doesn't go below 0, and they can do at most k sets of training in total. And given that, they want you to find the minimum possible score, and the score is defined as the longest time for an individual member to finish the food. So the statement can be a bit confusing, so I'm going to illustrate it with an example. So here we have 3 people, so one of them, so they have coefficient of 4, 2, and 1. Oops. And the plates of food have difficulty 2, 3, and 1. And so we can assign each person to eat one of the plates of food. So for example, let's just ignore the effect of training from for now, and we'll look at it later. So if we pretend we didn't have any training available, so if we have 4 and 2, then that would give us 8. So this is the time, this is the difficulty, and this is the coefficient, or I should use whatever they use. They use A and F. Okay. Oops. So this is A and this is F. So this is these are the times. So 4 times 2 is 8, 2 times 3 is 6, and 1 times 1 is 1. So they want to take the maximum time here. So in this case, that would be 8, but we can actually do better than this. So if we had an order like 4, 2, 1, and instead if we assign 4 to eat the plate of food with difficulty 1, and assign 2 to eat the plate of food with difficulty 2, and 1 to eat 3, instead what we're left with is 4 on the first, for the first person, 4 for the second person, and 3 for the third person. And so the maximum time among all these products would be 4. So we can see that this is better. So why is this order better than this order? And that's because we assign the large numbers to multiply by the small numbers. And since what we want is the maximum among all of the times, or among all of the products that we get, this is going to be optimal. So if we put 2 large numbers together, for example 4 and 3, we're going to get 12 as a product, and that's not good for us because it doesn't matter how small the other ones are. we're only going to look at the maximum. So 12 is already a bad score. So the intuition is that we should match the largest coefficient with the smallest difficulty, and the largest difficulty with the smallest, sorry, and the largest coefficient with the smallest difficulty. And so what we can do to achieve this is we can sort the first one in, let's say, increasing order, and we can sort the second one in decreasing order. That didn't do correctly. Okay, we can sort the second one in decreasing order, so that'll let us multiply these such that the maximum among all the products is minimal. Okay, and they said we can also do sets of training. So if we were to binary search, should I word this? Okay, so the effect of training is this. So I'll just rewrite it, actually. It's a bit messy. So in this case, they said you can do 5 sets of training. So if we order it like we described, so matching 4 with 1, and matching 2 with 2, and matching 1 with 3. So a set of training would decrease this 4 to a 3. So now instead of having a product of 4, we can have a product of 3. And we can also do another set of training to make this 2. So now our product is 2. And let's say we didn't do any set of training on this, the product would still be 4. So that's bad for us, because any set of training we did here would be meaningless, since this is a bigger value. So we're not going to do that. We're going to do 2 sets of training for this as well. So this would become 0, or 1 or 2, it doesn't matter. And we can also do a set of training here, and that will be 0. And so our maximum would be 2 in this case, after doing 2, 2, and 1 set of training. And so our total set of training is 5, and that satisfies this. And it gave us a smaller maximum, which is 2. And apparently you can't do a score of less than 2, so that would be our answer. So how we're going to solve this with binary search is we're going to binary search on the amount of time that it takes. So we're going to ask how many sets of training is necessary for the team to achieve a score of T. Should I use score or time? I'll use time. So to finish the food in T, is it minutes or seconds? I don't think it matters. In T, minutes. So we have to be able to calculate F at T. So for each member, we're going to have the product. So that's A at I times F at I. And so I'll name the function something else, like Fn, so that it doesn't conflict with this. So for each member, you know, the product is AI times Fi. So if this product is greater than the time we're given, then that means it can't finish the food in T minutes. So we're going to do training on it. And so we want to do the minimum training possible, such that AI times Fi is less than or equal to T minutes. So I'll just write it out like that. And so doing training is essentially decreasing the AI value. So let's say we want to find the minimum M such that AI minus M quantity times Fi is smaller than or equal to T. And so now let's just solve this equation in terms of M. So A at I minus M is smaller than or equal to T over F at I. And now let's add M to both sides and subtract T over F at I on both sides. So we get M is greater than or equal to a at I minus t over f at I. So if we want the minimum value of m that satisfies this, we just want m to be equal to a at I minus t over f at I. And when I do division here, what I mean is floor division, because doubles don't make sense in this question, since we're dealing with like time and product, and as also like a of I and m, they're all integers, so you can't have a decimal there. So you're gonna sum up. So fn at t would be the total of all m for each member. Okay, so let's go ahead and implement this solution. Oh wait, did I talk about how the binary search is going? I don't think I did. Okay, so since it returns in the sets of training that is necessary for the team to finish the food in T minutes. So if fn at t is greater than, or sorry, it's greater than k, then we can't finish in T minutes with k sets of training. And otherwise, if fn at t is smaller than or equal to k, then we can finish. Okay, and that's how we're gonna do our binary search. So, and we'll add the sorting process. So sort AI in non-decreasing order, and we're gonna sort fi in, actually, I'll just say sort f in non-increasing order. Okay, now I'm just going to implement this. So and n goes up to 2 times 10 to the 5, so that's 2e5. So we're going to sort the A array in increasing order. So remember how we sort. So we're going to sort from 0 to n minus 1, because that's where I place the elements. So a plus 0, a plus n. And we're going to sort the other one in decreasing order, or I should say non-increasing and non-decreasing. So sort f plus n, and we can put greater int, and that's going to indicate that we want it in decreasing order. So now let's do our binary search. So we can have our lower bound at 0 and our upper bound. So you know the maximum of AI goes up to 10 to the power of 6, and the maximum of fi goes up to 10 to the power of 6. And since the maximum time, so time is calculated by x times y. Oh, it does say seconds. Oops. Okay, so you know that it's the product of these, so you'll never need more time than 10 to the power of 12. And, whoops. 10 to the power of 12 doesn't actually fit into an integer, so later on we can just change them to long longs later. But for now I'm going to ignore that, and let's just begin our binary search process. So while low is smaller than or equal to high, we're going to have our middle value as low plus high over 2, and if function, which we have yet to define or initialize, the function of mid is greater than k, then it's not possible. Then we want to search for, actually this is somewhat counterintuitive. I'll say if it's smaller than or equal to k, then it can be completed. So we're going to lower our search space so we can try to search for a better time. So high is equal to mid minus 1, and answer is equal to mid. And otherwise we're going to say search for a larger time, so and see if that would fit. So low is equal to mid plus 1. and finally output the answer. Okay, so now let's define our function. So we have int function int time, let's just say t, and we're going to keep track of a variable total that's going to have the total of all our adjustments or the sets of training that we need. And for every member and food pair, we're going to say product, or actually I'll just say if ai times fi is greater than t, that means can't finish in time, right? So because the product is greater than the amount of time that we're given, so we need training, and so total would have to add on, as we solve for here, m is equal to ai minus t over f at I. And we're going to return the total. Okay, and as I said, this value might not fit into long longs, and also ai times fi, that might overflow into 10e12 as well, and also k goes up to 10 to the 18. So recall that ints only fit up to 2 times 10 to the 9 plus a little more, and then long longs can fit up to 10 to the power of 18 and a bit more than that. And so if we use long longs, we should be fine. So what you can do is you can replace every int here, or like every relevant integer here, and put a long long there. You can even do stuff like maybe define a long. So this is something that's very bad practice. So what this is saying is take every int inside of this program and turn it into a long. But you shouldn't do this because you might run out of memory, you might TLE, you might segmentation fault, and it might cause a lot of problems for you. So I can't legally recommend this, even though I do it a lot. So let's just say type def long ll, and so let's declare our variable types as long instead of int. So that should be all of them, I think. Okay, so let's try to submit that and see if it works. Okay, so that worked. Are there any questions as to how I did this problem? Okay, I don't see any questions. And this code will be posted on GitHub later. So if nobody has any questions, I'm going to move on to the main event of today. So the main topic that I wanted to get through is prefix summaries. So let's jump right into the first problem that's going to give us the motivation for using prefix summaries. So this is a short problem statement, and it says, given an array of n integers, your task is to process Q queries of the form, what is the sum of values in the range AB? Okay, so this looks like a very simple problem. So it says there are 8 numbers and 4 queries, and inside of this 3, 2, 4, 5, 1, 1, 5, 3, these are the numbers. And so when it says 2, 4, it just wants the numbers in the range 2 to 4 summed up. So 2 plus 4 plus 5, and that equals 11. And so that would be our answer here. And when it says, for example, 1, 8, then it wants the entire array. And so the sum of the entire array is, let's say, 5 plus 9, 14, plus 2, 16, plus 8, 24. So that would be the output here. So if we just try to write a naive program for this, so what we can do is, at first we might try to run a for loop for every single query. So I can demonstrate that. So let's have A is the array, and n goes up to 2 times 10 to the 5. Oh, I forgot to do this. So for each one, we can initialize a sum variable and just iterate from A to B. So let's declare AB and take that in from input. And if we loop, say, set I equals to A, and until I exceeds B, we're going to sum up the value in A of I. And output that sum. Okay, so this program would certainly work, but if we try to calculate the time complexity of this, what did I do? Oh, I should name this something different, is what it's saying. Whoops. Okay, so this would work, but if we try to calculate the time complexity of this program, so this is O of Q while loop, because we're doing one iteration per value of Q. And so this for loop, so it goes from A to B, but A can go as far left as 1, and B can go as far right as n. So the maximum distance between A and B, that would be n. So this is an O of n loop. And so the whole program here would be O of Qn. And so therefore, if we have 2 times 10 to the power of 5, and we multiply that by itself, and I'm doing that because it says both n and q go up to 2 times 10 to the 5. And so we would get something like 4 times 10 to the 10. And so that would exceed our approximate number of operations per second that we can do in C++, which is 10 to the power of 8. And so even if we try to, oh, I'm not logged in, that's interesting. Okay, and even if we try to submit this, so what file is that? 1646. In the worst case, we would be doing 4 times 10 to the power of 10, so it's pretty likely that this won't pass, right? So the second test case gave us the time limit exceeded verdict, so that means that our solution wasn't fast enough. And so we need to come up with a better way to answer these Q queries. So answering each query in O of n time is very bad. So what we're gonna notice is that if we want, I'll just write out the numbers over here. So 3, 2, 4, 5, 1, 1, 5, 3. If we want some interval, say if we want the numbers from 2 to 5, so this is 1, 2, whoops, that's 3. So the indices 1, 2, 3, 4, 5, 6, 7, 8. So if we want the sum of the numbers from 3 to 5, what we can say is that that's just the difference between the numbers, the sum of the numbers from 1 to 5, and the sum of the numbers from 1 to 2. So if we knew the sum of the numbers from 1 to 5, so 3 plus 2 plus 4 plus 5 plus 1, so that would be 15. And the sum of the numbers from 1 to 2, that's 3 plus 2 is 5. So 15 minus 5 gives us 10. And that actually would be the sum of 4 plus 5 plus 1. So every range or every subarray of this array is the large prefix sum subarray subtracting a smaller one to the left of it. So if we had this 15 pre-calculated and we had this 5 pre-calculated, we would have an O of 1 loop, or not a loop, an O of 1 operation to get this 10 value here. And so if we work with some variables instead of just numbers, so in the first, so let's say we had an array of A, B, C, D. I'll make a couple more. So if I wanted BCD, what I'm going to do is I'm going to pre-calculate an array that's the prefix sum up to that point. So let's say we had 0 at index 0, just to make our implementation easier later. We're going to say, so the first range is just the number itself. And the second range, AB, that's going to be this range, so A plus B. I should have made more room, but and the third range goes up to here, and we don't have to go back to A and say A plus B plus C. We're just going to look at the previous one here and just add on C to A plus B, so we have A plus B plus C. Okay, I'm just not going to worry about the alignment here. I'll just draw like straight lines to separate them. And for D, we're going to add on D to A plus B plus C plus D. And so on. I'm not going to do E and F. So if we wanted the interval BCD, what we would take is the large interval ABCD here, which is the prefix of the array, and we're going to subtract A, and what we're going to be left with is just the subarray range that we want. And we can see that A plus B plus C plus D, whoops, which is this value aligned with D. So if we take this, and we take this, and we subtract the A, what we're going to be left with is just B plus C plus D. Right, so this is the interval that we want. And so B plus D, C plus D will be the sum of the 3 elements here. Okay, so now let's actually do this on the real numbers. So I mean the actual numbers, not like real numbers as in decimals. Like so 3, 2, 4, 5, 1, 1, 5, 3. So this is our original array. Let's call it A. And our prefix summary, let's call it PSA. So let's start off with a 0 at index 0. So at the first index, we only have 3. On the second index, we're going to add on 2. On the third index, we're going to add 4 to 5, and we get 9. And we keep on adding to the element in the prefix summary to obtain the next element. So we have 14 here, 15, 16, and 5 added to 16 is 21, and 3 added to 21 is 24. So then, if we wanted to calculate the range 2, 4, actually let me index these. So 1, 2, 3, 4, 5, 6, 7, 8. So if I want the range 2, 4, that's PSA at 4. What this gives me is this entire range here. And what I want to do is subtract what's on the left of it. So I want to find out what this is. And thankfully that's another one of my prefix sum array indices that I can use. So that would be PSA at the element that is immediately to the left of the left border here. So if I want the values from 2 to 4, I would do 2 minus 1, which is 1. So PSA at 4, we have 14. PSA at 1, we have 3. We have 3. So our answer here would be 11. Right here. And that would be the correct sum for 2 plus 4 plus 5. Let's do another one. So it's not letting me undo, and I don't know why. Oh, it is. That's weird. Is there an eraser in this tool? Oh, it was just slow. Okay. Oh, that's not. Okay, whatever. I'll just redo it. So again, we have our original array. So 3, 2, 4, 5, 1, 1, 5, 3. And we're going to construct it by, first of all, having a 0 in front, and then adding it to the array element each time. So we have 3 at first, and 5, 9, 14, 15, 16, 21, and is this a 3? Yeah, I think it is. 24. So let's do another one. So that's 5, 6. So if I want the elements from 5 to 6, so there's 0, 1, 2, 3, 4, 5, 6. So I want this range. What that actually is the prefix here minus the prefix here. So we have PSA at 6 minus PSA at 5 minus 1. Notice how we're not subtracting the actual 5 itself because we have to include that element. So we're subtracting 1 to get whatever's on the left of it. So what we have then is our 6th element is this, 16. And 5 minus 1 is 4, so that's 14. And the difference there is 2. And that would be the correct sum for 1 plus 1. Now this is a very short interval. Now, and if you just loop through it, you would get the answer very fast as well. But if we have a very large interval, like for example the next one, which is 1, 8, what we would have is just PSA of 8 minus PSA of 1. Oh, I mean the PSA of 1 minus 1, which is 0. And so 24 minus 0 would give us 24. And so notice how we did that in constant time instead of having to loop through every single element in this array. So now we can try to implement a prefix sum array. So we're going to take in input the same way, but instead of processing the queries right away, I'm going to pre-process our prefix sum array. So let me declare another array called PSA. Now, you can actually do it in the same array, but just to make things clear, I'm going to use a separate array for my prefix sum array. So each index of the prefix sum array, the value in each index is just the sum of whatever is before added on to the current element. And so that's the entire construction of the prefix sum array. And instead of having a sum variable and writing all these for loops, what we can say is just we want the range from A to B. So that's the prefix sum array at B minus the prefix sum array at A minus 1. And so that would give us the correct answer as well. And also I forgot one thing when I did it last time was that I forgot that it could overflow 10 to the power of 9. And even though each individual x can only go up to 10 to the power of 9, we have 2 times 10 to the 5 elements, and if we add them up, that's certainly going to exceed the size of an integer, so we can just replace them with long longs. Okay, and if we recalculate the time complexity here, this is going to be an O of 1 operation. And we're still going to loop through the queries O of q times. So instead we have O of n plus O of n, which is, this is O of n, and this is O of n. And we're going to have an O of q loop. And so finally that's just n plus q. But so if we approximate how much that would take, so 2 times 10 to the 5 plus 2 times 10 to the 5, that would give us like 4 times 10 to the 5. And so that's way less than 10 to the power of 8, which is what we can run in 1 second. So this theoretically would run way faster than within a second. Okay, I'm gonna try to submit this now. Okay, and that got accepted, and it ran within 0.11 seconds. So it was a significant improvements from the O of QN solution that we had before. Okay, does anyone have any questions about prefix sum arrays? So this problem right here and how we use prefix sum arrays to optimize our queries. So if nobody has any questions, I'm going to move on to our second prefix sum array problem. Okay, so this problem statement is very long, so I'm just going to summarize it for you. Okay, so essentially it asks us, it gives us a string and it defines the integrity or something. yeah, the integrity of the substring. And what they mean by that is they want to count the number of G's in that substring. So for example, they use zero indexing here, but if they go 1 to 3, you can count that there are 2 G's. So they want you to output 2. And if you go from 2 to 9, which should be something like that, you can count 5 G's. And so they want you to output 5 in that case. And so how we can use prefix sums to solve this is, first notice that how we would solve this naively would be to iterate through this interval and add 1 whenever we encounter a G, and we're going to add 0 whenever we encounter anything else. So we're going to use something called a frequency array. So this is a very long string. I think I'm just going to copy the first, let's say 10 letters of it. So K, G, C, G, U, S. Okay, so I'm just going to copy this part of it. So this is our string. I should not put an S there. Okay, so from 1 to 3, it wants this interval here, so G, C, G. So whenever there's a G, we add 1, and whenever there's anything else, then we're going to not add 1. And in other words, we can just say we're going to add 0. And so a frequency array just puts a 1 whenever there's a G, and then whenever there isn't something that we want, we just put a 0. So in this case, we would have 1 at a G and a 0 at the C, and 1 at the other G, and so the sum of this would be 2. Okay, so now let's just compute the frequency array of this string. So this is not a G, we put a 0, this is a G, and we put a 1, and so on. So 0, 1, 0, 0, 1, 1, 1, 1. I really need to find out how to erase in this thing. I think it's this. Never mind then. Okay, I'll just do whatever. Oh, if I use a white brush, maybe that'll work. Oh wait, I don't even know how to change color. That's bad. Okay. Remove selection. Does this do anything? Okay, never mind. I'll just write it again. Okay, so we're going to put a 0 whenever there isn't a G and a 1 whenever there is. And to find out the range sum of a particular substring, then we're going to calculate a prefix sum array of this. So let's say this is the frequency array, this is the string, that's the string, and this is our prefix sum array. So we start off with a 0 in the beginning, and then we have 0, 1, 1, 1 plus 1 is 2, 2, 2, and now we have 3, 4, 5, 6. Okay, so if we want the ones from 1 to 3, we're gonna, so they want this interval. What that actually is just this large interval minus the small interval, which is just one element. So that's PSA at 3 minus PSA at 1 minus 1. And so at 3 we have 2 minus 0, and that'll give us 2, which is our answer here. And if we want the answer from 2 to 9, so 2 would be, yeah. Okay, so 2 to 9 would be this interval here. I should index these so it doesn't get confusing. I just wrote 6 twice. Okay, so from 2 to 9, it's this interval, but what we can say is that it's this large interval minus the small interval here. So that would be PSA at 9 minus PSA at 2 minus 1, which is PSA at 1. Okay, so now let's construct our frequency array as well as prefix sum array to solve this problem. So and what does the length go up to? Okay, 10 to the power of 5. So we have a choice between using a 1 index or 0 index array, and even though the problem does use 0 index strings and queries, I'm going to use 1 index because I think it's easier to work with. So the frequency of I plus 1 would be, so I'll write this in a comment. So if it's G, then we want it to be a 1. Otherwise, we want it to be a 0. So what we can say is that frequency at I plus 1 is S at I equals G. Whoops. So what this says is if it is equal to G, then this is going to return true, which has a value of 1. And otherwise, it's going to return false, which has a value of 0. So we can just set that equal to that. And let's now construct the prefix sum array. So prefix sum array at I is equal to the sum of prefix sum array at I minus 1 plus the frequency array at the current element. And now we can take in the queries. So I already declared it. They give us an interval from left to right, so let's say A, B. And since we're using 1 indexing, if you're using 0 indexing, you don't have to do this, but since we're using 1 indexing, we're going to increment both A and B. And then we're going to say the answer is PSA at B minus PSA at A minus 1. What did I do? I didn't output a new line. That's not good. Okay. So that would get us hopefully the correct answer. And if we calculate the time complexity of this, so we have linear with respect to the string length. Here we also have linear with respect to the string length. And here we have O of Q. And so our final complexity is n plus q, where n is the length of the string. And since they're both 10 to the power of 5, we know that this is going to fit pretty comfortably inside 1 second. So let's try to submit that. Okay, so that worked. Does anyone have any questions about how we constructed the frequency array or the prefix sum array on the frequency array? Okay, if not, if there's nothing, we're gonna go ahead and look at the two-dimensional version of prefix sum arrays. So this problem says you're given an n by n grid representing the map of a forest, and each square is either empty or contains a tree. The upper left square has coordinates 1, 1, and the lower right has coordinates n, n. And your task is to process Q queries of the form, how many trees are inside a given rectangle in this forest? So if we look at one of the samples here, so we'll do the same thing as we did in our previous problem. So if there's a dot, that means there's no tree, and if there's a star, then that means that there is a tree. So we can build kind of like a 2D frequency array here. So we have, wow, we have 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, and 1, 1, 1, 1. Okay, and the queries are in the form y1, x1, y2, x2. So for the query 2, 2, 3, 4, what they're saying is you start at the coordinate 2, 2, so that's this element, and 3, 4, you go to row 3 and element 4, and that would be your bottom right corner. And so they want the sum of this rectangle here, and so you see you have 3 1s, so the answer here is 3, and that would be the correct output. And for 3, 1, 3, 1, you go to row 3, you go to element 1, and that would just be, element 1 is this. Okay, and that would just be this one single rectangle here, and that would be 1, and 1, 1, 2, 2. You would start at 1, 1, and the bottom right is 2, 2, and you want this rectangle here. Okay, so how can we use the idea of prefix sum arrays to solve this? Now, if we do this without any prefix sum arrays, what this will be is the top left can be as far as 1, 1, and the top right can be as far as n, n. So in total, if we were to answer Q queries while looping through all the elements in the sub-rectangle here, you would have Q times n squared. And since n goes up to 1,000, Q goes up to 10 to the power of 5. 2 times 10 to the power of 5. So that multiplied by 10 to the power of 3 squared, that would be 2 times 10 to the power of 11. And so that's obviously way larger than 10 to the power of 8. And so that obviously won't pass. Another thing we can try to do is do prefix sum arrays on each row. And so on each row, if we have a prefix sum array, we would only have to iterate through the rows. So in that case, we would have Qn, but 2 times 10 to the power of 5 multiplied by 10 to the power of 3. That's around 2 times 10 to the power of 8, which may or may not pass. But considering we have all that overhead from the input and constructing the actual prefix sum array themselves, this is still not optimal. So we're going to try to come up with a better algorithm that's going to pass this and O of q time. So the idea is we're going to store in each cell, we're going to store the sum of the rectangle from 1, 1 to the current cell. So for this rectangle, or it's actually a square, but we have 0 here, and from 0 to 1 we're going to store 1, and here is still 1, but for this entire rectangle here the sum of is 2, so for this index we're going to store 2. And I'm going to construct the rest of the prefix summary like that. And so, whoops. So here we're going to have the rectangle that is here. So that'll give us a sum of 1. And so will this. Wow, it's not drawing. Why is it not drawing? Okay, there we go. We have a 1 and a 1 here. So the 1 will contribute to the sum here. And so will this. And we can just continue to make our square like that. So this rectangle here, we count 4 ones, so that's a 4, and here we count 6. And in this subarray, there's 5, and 1, 2, 3, 4, 5, 6. And here we get 1, 2, 3, 4, 5, 6, 7, 8. And here we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, is that right? Yeah, I think so. Okay, so now if we want to query for this rectangle right here, how can we use this grid to help us calculate this subrectangle, the sum here? Actually, I'm going to ask if any of you have any idea how to obtain this rectangle by using the prefix 2D prefix sum array right here. So remember, each cell here stores the sum of this rectangle, whose bottom right corner is this cell, and whose top left corner is at 1, 1. So for example, this 6 stores the sum of all of these. So does anyone know how I would get the sum for this sub-rectangle here, only using the values of the cells? Six minus 2 minus 1 plus 0. Okay, let me see what. Yeah, that would be correct. And I'm gonna try to follow his logic here. So he took this value, he subtracted this value and this value, and he added on this value. So the logic is that if we know this entire rectangle here and we want this rectangle, let's first subtract the value of this rectangle and this rectangle, and then since we subtracted the small rectangle twice, let's add this rectangle back. So that would be the meaning of 6 minus 2 minus 1 plus 0. I think that's what he said. Yeah. So if we actually calculate that, 6 minus 2 minus 1 plus 0, we would get 3. And indeed, we have three trees in this rectangle. And I found a good visualizing tool here. So say this is the rectangle we want is this subrectangle that's highlighted right here. So the top left corner has a 7, bottom right corner has a 3. What we can do is add on this entire rectangle here. So what we want is this rectangle here, but first we're going to add on this entire thing, and then we're going to subtract whatever's on top. So we don't need any of these cells, and we also don't need any of the cells on the left, and this would be our desired rectangle, but we subtracted this one twice, so we're going to add that back. And so how we get this rectangle is whatever's on the left and the top left diagonally, and if we add that back, we're going to get our result exactly without any overcounting or undercounting. Okay, and how are we going to calculate this effectively? And now, if for every element we're going to go back and count all the trees in that grid, that's obviously going to be very inefficient. So instead, we're going to use the exact same idea. So there's another tool here. So if I wanted the this entire rectangle that's highlighted right here, and I don't know what it is yet, I can use the prefix sum of this, adding on to the prefix sum of this. Now what this is right here is these are counted once, but since these overlap, these are counted twice. So what we need to do is subtract this once to make these all single counted, or counted properly. So now all of these elements are counted once. And so if we add on the array element at the end, that'll give us the value of this entire rectangle here. Okay, so let's try to implement this now. Okay, so we have N and Q, and let's make an array for the trees as well as a prefix. Actually, for this problem, I'm going to show you how we would construct a prefix sum array right on the spot, so without using another array. So well, first of all, we need to convert whatever this grid has into zeros and ones. So let's take an input of N and Q, and we can iterate through the rows. And since these are characters, I'm going to use strings. So I'm going to take an input into a string, and for each cell, so each ij pair, I'm going to say prefix sum array at that value. So remember that, so here I'm one indexing my 2D array, but the string will always be 0 indexed. So I need to subtract 1 from j to get the actual character. And if the character is a star, then this will return true and give us 1, and otherwise it's going to return false and give us 0. And so what we can do to construct our prefix sum array is say that prefix sum array plus equals, ij plus equals. So if we go back to whatever we had here, we needed to add this, subtract this, and so add this rectangle here. So that's prefix I minus 1 at j. So PSA I minus 1 at j, and also add on a prefix sum array at I at j minus 1, and so that would be this rectangle right here. And now we over counted this rectangle here, so now we need to subtract this rectangle, so we need to subtract PSA at I minus 1 at j minus 1. And finally, we need to add on to this array. So actually, instead of doing that, I could have just said plus whether this is a tree or not, and so that would construct our prefix sum array. Okay, and now for the queries, we have top left and bottom left corner. So y2, y1, y2, actually, what's the order that they give us? y1, x1, okay. And y2, x2. Oh, I'm using commas for some reason. Okay, and the way we're going to calculate it, I'm going to go back to that, to this widget. So we need to add on this entire rectangle, so that'll be PSA at y2 at x2. And we need to subtract this rectangle here. So that would be whatever the top left corner is, the y value minus 1, and then indexed at b. So that would be minus PSA at y1 minus 1 at x2. And symmetrically, we're also going to subtract y2 at x1 minus 1. And since we subtracted too much, we're going to add this rectangle back. So that would be PSA at y1 minus 1 at x1 minus 1. And that should give us the right answer. Oh, what did I do? Oh, I didn't put this in quotations. Oh, I did something bad. Okay, just to make sure I'm doing the prefix summary properly, I'm going to output each element inside of this prefix summary and to see what it actually constructed and whether it was the intended thing. And also I'll put this in. Oh, okay. I think adding these brackets made it work. That was kind of careless of me to not put brackets there, but yeah. Since we want this to be converted to a Boolean, and equals equals has I think lower precedence than the addition symbol, the addition operation, so it added everything and then checked whether it was equal to the star and returned the Boolean. But that's not what we want. We want to turn this into a Boolean and add it on to whatever was left there. So yeah, that was my mistake. And I'm going to try to submit this. Okay, that got accepted. Okay, are there any questions and use the 2D prefix summary to calculate the subrectangle sums? Okay, since there aren't any questions, I will be posting the links to all of these. Oh, I just realized I didn't share the link of the doc, but that's fine since there's not much on here. I guess I can share it now. Okay, so you can see here that this has the problems that we did today, and aside from this, which we haven't done yet, so check out Checkerboard Summation, and instead of should we do this together? Okay, actually we can. So it says you're given a checkerboard with m rows and n columns, and up to 100,000 of these cells have specified values written in them, and the rest are zeros. And they said you'll write a program that will answer some queries, and these are going to be rectangle queries, except there's a special condition that it wants you to find the alternating sum of all the numbers within the rectangle, delimited by those two squares. So what they mean is add up all the numbers in squares with the same color as the first square given, and subtract all the numbers with the opposite color. And so I guess I should use a sample to demonstrate what they mean. So they have a 3x3 grid. So at 1, 2, they have 5. Oh, they have it right here. I don't have to do that. Okay, so at 1, 2, they have 5. At 3, 1, they have -2. And at 2, 3, they have 11. And so their query asks for 2, 1, 3, 3. So 2, 1 is this, and 3, 3 is this. So they're asked to find this rectangle right here. And so the first square here would be, so they want the positive value of this square, and this square, and they want the negative value of this square, and this square. And so 11 minus -2 is 13. Okay, and how we're going to do this problem is if it ends, let's say the top left corner is indexed 1, 1. And so if, I guess I'll draw it out. So so this is 1, 2, 3, and this is 1, 2, 3. And so in a checkerboard pattern, so these would have the same color. So these would have the same color. And should I color them, I guess? Or actually I'll just put an X or something. So these have the same color. And these have another color, so these have the opposite color. And so what we can notice is whenever we have a square whose row and column sums up to an even number, that's going to be one of the colors. And if it sums up to an odd number, it's going to be the other color. So for example, 1 plus 2, that'll give us the white color. And 1 plus 1, that's a black color. 3 plus 3, that's also a black color. And so the square is black, the square is black, the square is white, and so on. You can see that this is true. And so what I'm going to do is I'm going to say whenever we're on, whenever the row plus column is equal to 0 mod 2, I'm going to have, whoops, I don't know how that happened. I'm going to put the positive value, and otherwise I'm going to put the negative value. And then whenever we receive a query for the rectangle, I'm just going to look at the first square. And if the first square is 0 mod 2, then our current subrectangle answer will be correct. And otherwise, if it's 1 mod 2, I'm going to say that it's wrong, and we're going to put a negative sign because it's the exact opposite of what it should be. And so if we multiply the answer by -1, it should be the correct answer. So let's implement this. So m and n go up to 3000. Let's name it board. Okay, so we have updates until 000. So first let's take in m and n, and then while true, we're going to make a while loop, and rcx, and it's going to terminate with 0. So I'm going to say if r is 0, then break. Otherwise, we're going to say board at r at c equals x. Okay, so now let's construct our prefix sum array. So for I equals 1, let's go down the rows and then go down the columns. And board at I at j, and we're going to do the thing where we use principle of inclusion exclusion, and so we're going to add board at I minus 1 at j, as well as board at I at j minus 1, which is the rectangle on top. I can go back to the visual to show what it's doing. So if we want this rectangle here, we're adding this, then adding this, then this is double counted, so we subtract this and we add the element itself. So we have the element itself in the grid already, so I'm just going to do plus equals. So the rectangle, this is on top, this is the rectangle to the right, and we double counted, so we subtract the rectangle on the top left, and that should give us the correct board. And for each of the queries, oh, I forgot to do the thing where I multiply that by -1 if it's if r plus c is 0 mod 2. So I mean if it's 1 mod 2. So if r plus c is mod 2 is equal to 0, then it's we want the positive one. So we're going to multiply that by 1. Otherwise, we're going to multiply that by -1. Oh, that should be a question mark. Okay, so this is the condition. So the condition, if this evaluates to 0, I mean this expression evaluates to 0, then it's going to multiply that by 1. Otherwise, it's going to multiply that by -1. And so when we answer our queries, how is it going to work? Oh, it's going to give us queries until zeros. So again, we can have a while true loop. So it's going to give us R1, R1, C1, R2, C2. Okay, so our answer would be the board at R2 at C2 minus the board at R2 at C1 minus 1 minus the board at R1 minus 1 at C2. And since we subtracted too much, we're going to add that back by adding board at R1 minus 1 at C1 minus 1. Okay, so now if R1 plus C1 is equal to oops, I should put brackets. So if R1 plus C1 mod 2 is equal to 0, then we know that we don't have to change our answer. Then let's just output our answer directly. And otherwise, we're going to output our answer multiplied by -1. Now obviously I could have done the same thing I did up there with the ternary operator, like with the conditionals, but I just wanted to write it out for this part to show you what I'm doing. And yeah, let's try that. I forgot to break if it gives zeros. So if R1 is equal to 0, then let's break out of the loop. Okay, let's try this. We need longs for this problem, I don't think, because the values are fairly small. Actually, do we need longs? I don't think we do. Okay, so that worked. Turns out we didn't need longs. And are there any questions about how I did this problem with the 2D prefix summaries? Okay, again, all of the code to all of these problems that we did today, they're going to be posted onto GitHub, so you can take a look at it later when we release it. And I think we're just going to end early today instead of moving on to something new. So try some of the practice problems if you have any time. You obviously don't have to do all of them, just try a couple if you want to. And yeah, if you have any questions that you come up with later, you can feel free to ask in the Discord server, and I'm going to leave you to practice on your own now. And yeah, so have a good day. Bye.